Welcome to the Explainer. Today, we're kicking off a massive, comprehensive journey. We are looking at a complete beginner's roadmap to demystifying machine learning and, more importantly, getting you totally career ready for the 2026 job market. Honestly, whether you're transitioning from a completely different field or you're literally just starting your tech journey today, this explainer is designed to take you from absolute zero all the way to deeply understanding the core mechanics of AI.
So let me ask you something. Ever wondered how Netflix knows exactly what you want to watch next? Or how your phone just automatically sorts photos of your friends without you doing a thing? It kind of feels like magic, right? Well, the truth is, it's absolutely not magic. It's actually driven by highly accessible algorithms and step-by-step processes that anyone, and I mean anyone, can learn. You don't need to be some math prodigy to figure this out. You really just need a logical mindset and a bit of curiosity.
Okay, let's dive into our roadmap for today. First, we'll cover what machine learning actually is. Second, supervised versus unsupervised learning. Third, we'll look at core machine learning algorithms. Fourth, the 5 steps to actually build a model. And finally, we'll map out your exact AI career roadmap.
All right, Section 1. What is machine learning? Let's break down the absolute core concepts without drowning in technical jargon. Before we even think about modern code, I want you to consider these words from Alan Turing, the legendary computer scientist. He said this decades ago. The foundational idea here, that a machine could learn patterns and actually add to its own knowledge rather than just blindly following rigid line-by-line commands, has literally been the North Star of computer science for a very, very long time. And that brings us perfectly to our formal definition. Machine learning is a subset of artificial intelligence. It focuses on algorithms that learn patterns from training data to make inferences and predictions on completely new data. Notice that last part, without explicit, hard-coded instructions. The whole goal here isn't just crunching historical numbers, it's about generalization. We want the model to apply the patterns it learned to totally new, unseen, real-world situations. I love this analogy because it brilliantly illustrates how you can wrap your head around the whole process. Think of machine learning exactly like baking a cake. Your raw ingredients, that's your raw data. The recipe you follow is your algorithm. The utensils that make the whole process easier are your Python modules, like scikit-learn or pandas. The oven, where the actual transformation happens, is the model training phase. And finally, the taste testing. That's your model evaluation. Your raw, messy data transforms into a valuable, actionable insight, just like a bunch of flour and eggs becomes a delicious cake. Moving on to Section 2, supervised versus unsupervised learning. This is all about how we actually teach these algorithms. The crucial difference here really comes down to human guidance. Supervised learning relies heavily on us. We feed it labeled inputs and outputs, like showing it thousands of pictures explicitly labeled as either apples or oranges so it learns the difference. Unsupervised learning, on the other hand, is given a huge pile of unlabeled data. It has to discover the hidden structures entirely on its own. It's like automatically grouping online shoppers based on their habits without anyone telling it what those groups should even look like beforehand. Now, if you're working in supervised learning, which, by the way, most beginners do, you are generally going to be solving one of 2 very specific types of problems: classification or regression. Classification assigns data to discrete categories. Think of your email automatically filtering messages into a spam folder or your main inbox. Regression, though, is all about predicting a continuous numerical value. So that would be forecasting next quarter's sales revenue, or, say, predicting the exact length of a salmon based on its age and weight. All right, Section 3, core machine learning algorithms. Let's look at the actual mathematical tools, the recipes, used in the industry. First up, we have linear regression. This is absolutely one of the most foundational algorithms in data science. It basically computes a weighted sum of your input variables to fit a straight line right through your data. It is incredibly useful for regression tasks, like predicting a general stock price trend over time. It's simple, it's fast, and it gives you a really strong baseline prediction to work from. Next, we've got decision trees. You can think of this one like a giant flowchart. It splits data step by step based on very specific criteria, asking questions like, is the petal length greater than 2 centimeters? Until it reaches a final prediction. Now, while this is incredibly intuitive and easy for us humans to read, a major drawback is that a single tree is highly prone to what we call overfitting. That basically means it memorizes the training data way too perfectly and then completely fails when you show it new data. So the crucial point here is that we need a way to fix the weaknesses of that single, fragile decision tree. Enter the random forest. This is what's known as an ensemble algorithm. Instead of relying on one tree, it builds a massive forest of them. Each individual tree makes its own prediction, and then they all effectively vote on the final output. By relying on the wisdom of the crowd, a random forest gives you a significantly more accurate and robust result.
And finally, the heavy hitter, the driving force behind modern deep learning, the artificial neural network. It's a highly complex model made of interconnected nodes, totally inspired by the neurons in a biological brain. These nodes pass mathematical signals back and forth to approximate crazy complex nonlinear functions. Now, while these are incredibly powerful, they power things like advanced image recognition and ChatGPT, they are often considered black boxes because tracing exactly how they made a decision internally is notoriously difficult.
Section 4. 5 steps to build models. Let's take all this theory and look at how it's practically applied. Believe it or not, building a model almost always follows this super straightforward 5-step workflow. 1. Load your data. 2. Explore your data. 3. Split your data into a training set and a testing set. 4. Train the model using that training set. And 5. Evaluate its performance on the unseen test set. What is genuinely amazing is that, thanks to modern Python libraries, you can sometimes execute this entire workflow in literally just 5 lines of code. No joke. But let's hit pause and zoom in on step 2 for a second. Exploratory data analysis, or EDA. This is where you roll up your sleeves to clean messy data, handle missing values, scale variables, and visualize trends using tools like Matplotlib. I really cannot stress this enough. Most machine learning models in the real world fail. But they don't fail because the algorithm was wrong. They fail because the underlying data was misunderstood, dirty, or just poorly prepared. Great machine learning absolutely starts with great data handling. Here's a wild stat to put that into perspective. A staggering 80% of your time as a practitioner will be spent right here, prepping data. Everyone always wants to jump straight to the sexy neural networks, but the real undeniable value is created in how well you prepare your data. If you can master data handling early on, you are automatically miles ahead of the vast majority of beginners in this field. Finally, Section 5, your AI career roadmap. Let's map out exactly what you need to study to become an ML engineer by 2026. First things first, let's bust a massive myth right off the bat. You absolutely do not need a traditional computer science degree to learn ML. The reality is that successful professionals in this field come from incredibly diverse backgrounds. We're talking mechanical engineering, finance, even the arts. What you actually need is a logical mindset, a whole lot of patience to debug your code, and a deep comfort with continuous self-learning. So here is your definitive checklist for 2026. For programming, you need to focus on Python and its core data libraries, NumPy and Pandas. For mathematics, you need a solid functional understanding of linear algebra, probability, statistics, and calculus. Now, you might be asking, why the math? Well, math gives you the edge to actually understand why a model behaves the way it does. It prevents you from treating AI like a magic black box. And finally, you've got to get totally comfortable with essential tools like Jupyter Notebooks, Google Colab, and GitHub for version control. To actually become job ready, you have to prove your skills. Don't just do tutorials. Work with real-world, messy datasets from platforms like Kaggle. Build end-to-end pipelines, what the industry calls MLOps, from data ingestion all the way to deployment. You want to showcase a really diverse portfolio of projects, ranging from simple classification to natural language processing. And crucially, document every single thing clearly on your GitHub so recruiters can see exactly how you solve problems. In 2026, a hands-on portfolio beats a resume full of buzzwords every single time. And that brings us to the end of our beginner's roadmap. The foundational concepts make sense, the tools like Python and scikit-learn are ready to be downloaded, and your learning roadmap for the next few years is crystal clear. So the only real question left to ask you is this: what real-world problem are you going to choose to solve first with machine learning? Thanks for joining me on The Explainer, and keep building.